Are you broadcasting? Oh,
Yes,
okay, I see it now. Okay, thank you.
we have a little lag time between here and YouTube. Okay, I think we can start. I'll just do a short introduction and then I will pass you the floor. Okay, Kim? Alex?
Got it.
Okay. Oh, hello, everyone who joined us here in Zoom and also on YouTube. Welcome to another talk in our webinar series. I'd like to remember that this webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, LIneA MCTI. Today, we have Alex Kim from the Lawrence Berkeley National Laboratory talking about peculiar velocity surveys from the Zwicky Transient Facility and the Rubin Observatory. Alex, thank you very much for accepting our invitation and being with us today. The floor is yours.
Thank you. I'm going to share my screen. And I hope that you can hear me. And thank you again for the invitation. I think many of you were not around 5 years ago, or maybe have forgotten, but I think it was about 5 years ago that I gave a presentation to this very same seminar series. And I remember back then when I received the invitation, how excited I was that I'd be able to speak to you about the science. But then the grave disappointment that I had when I realized that the meeting was virtual and that I would not be going to Brazil. But this time I got the invitation. I was happy to be able to speak to you, and I don't have the disappointment because I knew that the meeting was going to be virtual. So before I go into the more scientific part of the presentation, I wanted to give you a little bit of background. So in the United States, the cosmology, the field of cosmology is basically supported by two different groups. The the astronomers and the high energy physics community. And also there are two major funding agencies, the National Science Foundation, NSF, and the Department of Energy, DOE. And both of those agencies fund kind of both activities, although NSF funds more of the astronomy and DOE funds more of the HEP, or the high energy physics. And basically both of those, both communities, the astronomy community and the high energy physics community, around every 10 years comes up with a plan for how they want to proceed in the long-term future. And this is basically where large projects come up and get supported. On the astronomy side, it's called the Decadal Survey. And that actually, a lot of the activity of that from the community side occurred last year. And my understanding is that that Decadal Survey Committee is actually has written a lot of their report, although that report has not become public yet. On the high energy physics side, the process is called SNOMAS. The reason is that it used to be held in a Colorado resort called SNOMAS, but it's no longer being held at SNOMAS, but it's still called SNOMAS. And we are right now in the middle of that process. And the first part of the process is basically soliciting information from the entire high energy physics community, trying to find out what kind of new projects people are interested in working on, and try to advocate to our HEP colleagues that this is kind of work and science that we want to do. And then the next step of that is to take this information, make a report. The report goes to another committee called the P5 committee, and they actually make recommendations to the funding agencies as to how to spend their money, which projects that they feel like the community advocates. So as part of this process, I have been trying to advocate both in the Decadal Survey and in the high energy physics side, on the SNOMAS side, the interest of supernova peculiar velocities, and particularly the connection to cosmology and fundamental physics. And even though I'm doing this kind of in the US community, I think it's very important. It's a good opportunity to share this with you in Brazil, because really in Brazil, you do have a long history of working on peculiar velocity surveys. And also right now, there's activity on the theory side in Brazil in terms of supernova peculiar velocity surveys. And there are telescope resources that you have. So kind of the purpose of this presentation is not to say that I'm doing anything fantastic or great or have any great results to show you, but I do hope to get you interested and energized and thinking about you yourselves joining into this kind of science. Okay, so given that introduction, I will be talking about supernova peculiar velocity surveys. And given this audience, I think you don't need that much introduction. But I think one thing that a lot of the astronomers and cosmologists know are that galaxy positions are a very powerful probe of dark energy and gravity. And the cartoon of this is presented here. On the left-hand side, there's a picture of the cosmic microwave background, a picture of the energy density fluctuations in the very early universe. And an experiment like Planck has actually measured the amplitude and the clumpiness of these energy density fluctuations very precisely. Now we can take our theories, basically our theory of gravity, our understanding of the background expansion, and also of the geometry of the universe, and actually calculate how we expect these amplitudes and clumpinesses to evolve into densities in the universe, more local universe, the universe that we can observe. In particular, we observe them by looking at galaxies here or at the Lyman alpha forest. So that's a connection between galaxy positions and the CMB are connected through gravity and cosmology. And this is very well understood and has motivated lots of funding by the agencies in this activity. The most current example is DESI, which unfortunately, I think if it were not for COVID, DESI would be running at the moment. things have been slowed down, but I think we're trying to ramp up again right now. It's being run in Arizona at the Peak 4-meter telescope. The focal plane is 5,000 fiber positioners, which will put fibers onto galaxy positions so that we can get spectra of thousands and thousands and thousands of galaxies in one shot. And the objective of this is to measure the positions of these galaxies, both in angular and in terms of the redshift, and do cosmology. And in this particular example, I show kind of projections of what DESI can do with a BAO measurement. So basically measuring the scale or the expansion rate of the universe as a function of redshift. So that's kind of the present. I just mentioned snow mass, and there's a lot of interest in the community about what the next generation spectroscopic survey is going to look like. And here I've just clipped and pasted a few of the cover pages of snow mass letters of interest, expressing interest in making like a larger aperture telescope, going from 4 meters to say 10 plus meter 10 meter telescopes, and also increasing the number of fibers that are put onto the focal plane to make more efficient the collection of galaxy spectra. So this is very well established that galaxy positions and are a very interesting probe of cosmology. But of course, galaxy positions and velocities are related. The initial universe was very homogeneous. Now it's not so homogeneous. Galaxies have to move from point A to point B to clump up. And to get from point A to point B, things have to move. So that motion that's kind of on top of the cosmological expansion is peculiar velocity. So if this next movie works, hopefully my bandwidth is good enough. This is a movie from the Millennium simulation of the motion of dark matter. And the initial condition is something like what the CMB has, small density inhomogeneities, and that will start to evolve. So they're very small, so you can't really notice them by eye. And then they start to evolve and to form the structures that we actually see. And of course, this evolution that we see is mostly dominated by gravity. And for those of you who have discerning eyes, you can see that these particles are moving to get to the position. So there's that example. And also you can notice that the more dense areas have higher velocities, which makes complete sense. So there is this fundamental connection between positions of galaxies and the velocities of galaxies. And so if you are a believer and say galaxy surveys, are a powerful probe of the growth of structure, and that we must build the next generation projects and facilities to study them in the next decade, if you say, well, galaxy positions and their peculiar velocities basically share the same cosmological information, really it's a conservation of mass thing here, which is this continuity equation, a connection between densities and velocities. So by the law of transitivity, you would say that, well, peculiar velocities are also a powerful probe of the growth of structure, gravity, and the primordial universe, and that we really should be pursuing projects on them in the next decade. And the answer is, of course, that we are. I mean, peculiar velocities are motivating projects today, and the prime example of that is redshift space distortions. So one of the assumptions about our universe is that it's homogeneous and isotropic, that there's no preferred direction in the sky, in the universe, so that if you make a calculation of the correlation function between galaxies, just where the positions of galaxies relative to each other, you would expect to see a radial symmetry. And that's what's shown here on the left-hand side in real space, a correlation function along the line of sight and along the perpendicular, the tangential direction. And you see that this is from a simulation, but you can see that this is radial. But in reality, one of the most difficult things in astronomy is to actually measure a radial distance. So even though on the angular side, we can measure angles pretty well, in place of a distance, we actually measure redshift. And what we find is that due to the fact that we're measuring redshift, which has a combination of the expansion history and this motion due to gravitational attraction of local overdensities, that this symmetry here is broken. And so you can actually glean a lot of cosmology out by looking at the shape of this particular plot on the right. There's the Alcock-Paczynski relation, which basically describes the entire kind of general shape of this. There's kind of the inflow of galaxies towards each other when you have, well, basically due to the gravitational attraction, which causes some compression of this shape. And then once you get into galaxy clusters, you get these very sharp fingers of God here, where basically you're not really measuring the cosmological expansion anymore. You're looking at basically virial velocities due to thermally stable cluster. Okay. And there are measurements of this. And just recently, I think it was just maybe 3 or 4 months ago, the EBOS survey put out their latest, their results, their cosmology results. And this is a plot stolen from the presentation by Kyle Dawson. And in their plot, they have 2 major results. One of them is of the expansion history. So this is a BAO measurement, but the second one is of the growth, or the peculiar velocity measurement, really is what this is, or the redshift space distortion. And I'll just note right now, for those of you who are not totally familiar with the terminology, is that there is this kind of magic parameter combination called F sigma 8. And that's something that we use to parameterize the peculiar velocity. In a few slides, I will be making a connection between that and real physics. Okay, so this is just to emphasize that, you know, for EBOS and for these surveys that are going on and are being planned in the future, things like redshift space distortions are viewed as important scientific result as just the original kind of BAO measurements. Now, in the next slide, I'm going to show another slide that was shown by Kyle, and it's basically the same information, except before plotted was F sigma 8, but now what's plotted is F sigma 8 divided by some kind of, the F sigma 8 defined by some fiducial cosmology. And what that fiducial cosmology is lambda CDM. And here's a plot of the same data as a function of redshift. And so this is basically 1 for right here for the lambda CDM case. And what's been done is other models have been considered where you take lambda CDM and add 1 more extra parameter. Like, for example, instead of having a closed universe, I make the universe opens. So you have to understand what the geometry of the universe is. Or if you add a W, non-trivial W, or a cosmological constant, for example. And you can see how by making the your cosmological assumptions a little bit more complicated, with 1 more degree of freedom, how this curve is expected to change. And I think the real points that I want for you to come out with this from this particular plot is that these different models, adding that extra degree of freedom, really causes a divergence at low redshift. Basically, the idea is that a lot of these models are tied in at the CMB at high redshift. You have to let the universe evolve. So it's at the recent universe where you can actually have the most leverage in making the distinction between these different models. Another thing to mention is that the error bar from the measurement from EBOS, from redshift space distortions, is quite large here at low redshift. And that's because there's a very small amount of volume here in which you can probe. And the redshift space distortion is a statistical measurement. And the more volume that you have, the more better that you can constrain this measurement. In the local universe, you have a finite volume available, you have a large error bar. And this is a little bit of a deviation, but kind of the converse of what I'm saying is actually motivating a lot of thought in going to the very high universe, where you can actually get extremely a large volume and an extremely large number of K modes. So there's also a lot of interest in pursuing cosmology at the very high redshifts. But I'm going to be focusing here on the low redshifts. Okay, so I just presented redshift space distortions as an example of how peculiar velocities are being measured. But there's another way of doing them, getting peculiar velocities, and it is through using peculiar magnitudes or distances. And just to give you an idea of what the idea is that if you have a perfect standard candle, you can plot their Hubble diagram. And here's a toy example of that. And what you see here is that if you measure a bunch of these standard candles with no noise, you get this wonderfully straight Hubble relationship here. Okay. So this here, I've used Z as a measurement of the cosmological redshift. However, if you now consider the fact that there may be some local densities or local overdensities or underdensities, then there could be motion on top of that cosmological expansion. So if you make a plot of the Hubble diagram, but now replacing this cosmological redshift with the observed redshift, you'll actually start to see deviations from this Hubble relationship. And usually in the supernova cosmology, when we see deviations from a Hubble relationship, we think, there's something wrong with the standard candle. And there's some kind of intrinsic dispersion in the luminosities of the standard candle. But in this case, we're looking at dispersions and interpreting them as peculiar velocities. Another thing that you can notice here is that at low redshift, the size of the effect is much larger at high redshift. And that's just related to the fact that given a fixed velocity uncertainty, the translation into the propagation of errors in terms of the redshift goes linearly with distance. So in order to use these kind of standard candle methods, you really have to focus at the low redshifts. And here's a little bit of math that translates between the two. Now, practically speaking, we can look at the exact same Hubble diagram and translate them in terms of peculiar magnitudes. And so deviations in this axis rather than in this axis. This is, I think, maybe you could say it's either an irrelevant point or a subtle point, but the community mostly talks in terms of peculiar velocities. But in practice, really what we do is work with peculiar magnitudes or peculiar distances. So I may switch in between the two different terminologies in my presentation. But I will say that there are a couple of points to emphasize that make the fact that peculiar magnitudes and not peculiar velocities are what we're looking at. The first thing is that when we're working with standard candles, we generally have large uncertainty on the distances, but basically effectively zero uncertainty on the redshift errors. So it just makes making deviations along this axis a lot easier to handle. And then the second one, which I think maybe is a little bit subtle, but I'll mention that actually, I said that the magic parameter is F sigma 8. And in reality, if you do the mathematics to first order, peculiar velocities are proportional to H F sigma 8. So there's also this Hubble parameter that comes into this combination. But when you actually kind of do the math of transforming between velocities and magnitudes, and because magnitudes has a distance piece in there, there's an actually cancellation of this H, so that you do have this pure measurement of F sigma 8. So I've had conversations with my colleagues at LBL about this, trying to understand why is this measurement doesn't depend on H. It's because of this cancellation here. Okay, so I just said that if you have a good distance probe, you can start to measure peculiar velocities, and a lot of people are doing this. And the main probes that people are using are galaxies, using two different kinds of methods. One is with spiral galaxies, using the Tully-Fisher relationship. So what I did here is I kind of put in red here an observable that we can see that doesn't depend on the distance. So we can look at the rotation speed of the spiral arms of a galaxy. And there's a relationship between that and the luminosity. So if we look at the brightness and the luminosity, we can figure out what the distance is of that galaxy. Another technique is to use early type galaxies, something called the fundamental plane. And again, there are a couple of observables that you can see that are really distance independent to first order, the velocity, dispersion, and the surface brightness. And then there's a connection between that and the radius, the size of the galaxy. There are physics reasons to believe in these relationships. This is just kind of rotation, gravity. This is basically, if you imagine that the stars in an elliptical are virialized. But the relationships between, the connection between physics is not perfect. And in both of these relations, you basically get per galaxy at 20% a distance uncertainty. And here are some very recent results using fundamental plane galaxies using the 6DF survey. One thing you can see is that you can't, they don't go very deep. They only go out to a redshift of 0.057. And the current measurements that they get are at this level. You'll notice that the systematic errors are quite significant here. And the size of the error bars are giving you basically something like, if you combine these together, a 20% uncertainty. And so here's a plot from this paper by Adams and Blake, and this is their particular result here. Here, these delta-delta points here represent measurements of redshift space distortions using the exact same data. Okay, so this is redshift space distortions. This is using peculiar velocities. And one, I guess, important point that I want to point out here is that there's actually 3 of these blue points here. This one here is if you use these galaxies only using redshift space distortions. This is if you use only the peculiar velocities of these galaxies. But you can combine these 2 pieces of information because obviously the density field and these galaxies live in the same volume. They both are experiencing the same underlying density field, so that the densities and the velocities must be correlated. So there's something called sample variance. If you have a single measurement here, you suffer through sample variance. But if you take into account that these objects, the velocities and the densities are in the same volume, that sample variance cancels out. And you can combine those 2 pieces of information to get a much smaller error bar. So in the projections that I'll be presenting, even though I say it's a peculiar velocity or a peculiar distance measurement, you are taking advantage of the fact that you also have some information of the density field with those very tracers. Okay. So I just presented a recent work, kind of the state of the art work based on galaxy distance indicators. And now I'm going to talk about type 1a supernovae as distance indicators and how they can outperform the Tully-Fisher and the fundamental plane techniques. So if you do kind of the back of the envelope calculation, comparing how well one peculiar velocity survey does compared to another one, kind of the main parameters that you care about the survey is the amount of solid angle of sky that you cover, how deep you go, and then this combination. It's a combination of the distance precision squared divided by the number density of sources. And really, it is now in this kind of generation of supernova surveys that these kinds of numbers are going to be competitive and actually well surpass those from the galaxy distances. So why now? It's based on, supernovae are much better distance indicators than galaxies. So if you have 1 supernova, that's the equivalent of 30 fundamental plane galaxies. And the next thing is what I just mentioned, that these new surveys that are coming up are going to be coming up with numbers, densities of supernovae that are competitive in solid angle, depth, and in number density. So I'll just go into each of those points briefly. First, in terms of right now, there's a lot of work in trying to improve type 1a supernovae as distance indicators or peculiar velocity indicators. And on the left, there is a plot of how we currently, or I guess the most standard way in which we try to standardize type 1a supernovae. So if you look at the top plot, there are a bunch of light curves, the evolution of the supernova brightness as a function of time. And you see that to first order these supernovae, okay, so plotted in the different colors are different supernovae. What you see is that there is some diversity in these light curve shapes and also in the brightness. But you notice that if you actually, well, I guess if you have a good eye, you can see that the narrower light curves are fainter than the broader light curves. So you can make a correction and standardize supernovae based on their light curve shapes. And using kind of the state-of-the-art techniques, using multiple bands, good, well-sampled light curves, we can actually standardize supernovae to about 12 to 6% in distance, which is 0.12 magnitudes, okay, a magnitude dispersion. However, there's new work. Well, actually, I wouldn't say that this is so much new work, but there's a lot of, there's this idea in the past, which is being validated at the moment, which is that instead of standardizing supernova based on their light curve shape, like we did here, you can actually do much better in terms of standardizing objects based on their spectra. So supernova spectra, you know, they all kind of look the same, but they don't all look perfectly the same. And if you take a supernovae whose spectra look very similar to each other, you find that they actually have very much more similar distances than if you just take a random type, another type 1a supernova. So the current results seem to indicate that there is a, if you use a spectroscopic technique, that you can get 4% distance precisions relative to the 6% distance precisions here. And this actually is quite significant because if you remember the previous slide, the quality of a survey goes as the distance uncertainty squared. So this makes a single supernova much more powerful. Okay, okay. And if you want some stories about how I made this plot a long time ago, I'll tell you that offline. I was going to say something about that. But I will continue on with a description of LSST, but also there's, or which I guess is the Rubin Observatory now. Sorry, I didn't change these slides. And really what these kind of surveys are going to do is for free, provide basically all discoverable type 1a supernovae that are local. So for those of you who are not as familiar with ZTF, ZTF is a wide field imaging survey that's being run in Palomar, so it's in the Northern Hemisphere. And they're just finishing up now, and I think are about to start now ZTF-II, which is the second generation. And I think for 3 years, okay, maybe I wrote this down wrong. It may be 3 or 4 years, they're going to be continuing to discover supernovae in the northern sky out to a redshift completeness, with completeness out to a redshift of 0.09. Something that may be more familiar to people is the Rubin Observatory, the LSST, which will be discovering supernovae in the southern sky for 10 years at the level of, 10 to the 50,000 supernovae out to a redshift of 0.15. And just to give you an idea of why this is such a giant leap in supernova discoveries, plotted below here is kind of what this, in this kind of reddish color here, is kind of the number density as a function of redshift of the number of supernovae that we have available now. And in yellow is what we expect LSST to provide. So it really is orders of magnitude more supernovae. So if you take those two things together, the improvement in the distances of supernovae, and also the fact that you're going to get a large number of these objects, you can do a comparison of what supernova can do and what you can do with a fundamental plane survey. So here, I'm going to describe TAIPAN a little bit in a moment, but TAIPAN is kind of the next generation fundamental plane survey. And if you just take this metric, you get this kind of number here. And the problem is that you have, even though you have lots of galaxies, each of them has a large uncertainty in terms of their distance. If you compare that with the supernovae, you see that already the supernovae are, with the number density of LSST, is much more better performing, much more powerful than what you can do with a fundamental plane survey. And as a side note, I'll also mention that there's a finite number of galaxies out there. So, you know, TAIPAN, they can run, and then basically after they're done because there's no more galaxies to look at. You can't improve N. Whereas for the very patient, for supernovae, N is basically infinite. You just keep on observing more supernovae go up. So you can actually improve this number basically as much as you want, if you're patient. So based on this kind of interest, we made some projections for how well we can measure F sigma 8 at the Rubin Observatory. And these red points basically correspond to kind of what I showed you before from the Adams and Blake paper, which is kind of the combined peculiar velocity redshift-based distortion measurement from type 1a supernovae. And the kind of one thing that you can see is that you can actually go up to significant redshifts here, and you will be able to get sub 10% precisions in multiple redshift bins. So you can make a significant improvement to what current measurements have at the moment. Now, I think that this audience is quite savvy, but when I was trying to make this presentation, you know, one thing I have to do is convince high energy physicists that this is fundamental physics. And so, you know, you look at a plot like this and you say, oh, you know, F sigma 8, you measure it well. What do I care about F sigma 8? And I want to emphasize here that F sigma 8 really is a probe of fundamental physics. And that the evolution of the sigma 8 depends on gravity. Okay. And so this really is a probe of gravity. And there was an excellent empirical parameterization that was discovered by Eric Linder, which is a relationship between F and F, which is, I guess I didn't just define what F is, but I'm assuming that all of you know what F is. That is related to the matter density to the power of gamma, where gamma is a free parameter which depends on the gravity model. Okay. So for general relativity, Linder found that gamma is equal to 0.55. And then also he considered a couple of other gravity models and found that this gamma parameter changes for those different, for those models. So that if you're able to measure gamma through this F sigma 8, and this is how the relationship between this F sigma 8 and the gamma, you can actually distinguish between these gravity models. And given these kind of fiducial points here, 0.55, 0.42, 0.68, you can say, okay, what I want to do is resolve differences of gamma at this level, 0.13, to be able to distinguish between these models. And just to kind of visualize that for you, I guess I should have wrote this FD means F sigma 8. I'm sorry about the inconsistent notation here, but imagine that this said F sigma 8. This is a plot that shows how this F sigma 8 changes as you vary the value of gamma. And so I think there's a couple of things that I did want to point out on this plot here. One of them is basically it's the same information that I showed you from the EBOS plot, that really the probative power that you have is at low redshift. It's at low redshift where these curves really start to diverge here. Another thing that I will point out is that not only does the amplitude change, but the shape of these curves change. Okay, I shouldn't say the shape of the curve changes, but the location of the peak of the curve changes. So that here you notice the peak is at this lower redshift, whereas at this value of gamma is at a higher redshift. So there's actually information in the amplitude, but there's also information in the shape of this curve, which actually I have a backup slide on this, but it indicates that there's a complementarity between measuring F sigma 8 at low redshift with, let's say, distance indicators, and measuring them at high redshift with redshift space distortions. There's a little bit extra leverage that you have in there in doing a combined analysis. So what I did is I made some projections for gamma, making different assumptions about what kind of survey you have, how well you measure the distances to the supernovae, the number densities of things. And so on the left-hand side, I show what we can do kind of in the short term with something like ZTF-II and just using information from a supernova over 4 years. And these are the projections that I get here from ZTF supernovae. And just for reference, here is what TAIPAN, the next generation fundamental plane survey, is expecting to get. And you see that actually the supernovae in this kind of near-term survey will outperform what you can do with this upcoming fundamental plane survey. And to help you discern really what all these numbers mean, basically a reasonable range of expectation for the survey parameters will give you a 2 to 3 sigma distinguishing power between those gravitational models that I showed you before. Now, if you think more ambitiously for a long-term project like LSST, where the number density of objects really is going to be shooting up, again, what I have done is made this as a plot of the precision of the distances that you get of the supernova and also of the redshift maximum that you go. You can see that you can start to get 4 to 5 sigma distinguishing power between those gravitational models. So this is the excitement that I want to bring to you and also to the high energy physics community. And I guess maybe one minor thing that I will mention is that here I assume that you're following up basically all the supernova discoveries and you're measuring all of them very quite precisely. You can actually add a lot of slop. You can, what I mean is that even if you only follow up half of these supernovae, or if you don't measure them that well, you won't get the 4 to 5 sigma measurement, but you'll still get maybe a 3 to 4 sigma measurement, which will still be very interesting. So this is kind of the ambitious view of what you could do with LSST supernovae. So I just said that there are going to be these surveys that for free are going to be providing type 1a supernova discoveries. But we need resources beyond just those wide field imaging surveys. And just to kind of motivate that, I'll say one thing about LSST. The fiducial LSST survey strategy actually does not provide precision light curves. So on the left-hand side is kind of the nominal Rubin search strategy, simulation of a supernova light curve based on the observations from the nominal Rubin strategy. And you can see that actually in each of these bands, the supernova is not actually observed that frequently. And what happens is that in particular, if you have this kind of poor sampling, the color of the supernova is very poorly measured. And it turns out in terms of doing supernova cosmology, the color is very important because it's an indicator of how much dust extinction that the supernova experienced, and then dust extinction leads to a magnitude correction to correct for the absorption of that dust. So calculations have shown that the baseline strategy gives actually quite unusable distances for supernovae. So in the DESC, LSST, DESC collaboration, we've made a proposal for higher sampled light curves. And we won't know for a while exactly what will happen in terms of that strategy. The Rubin Observatory has formed a committee to make a recommendation on what that observing strategy will be, but we won't know for over a year on that. And if I remember correctly, I think maybe Peter Nugent may be the next speaker after me in this seminar series. And he's going to be talking about LS4 which is kind of a proposal to ensure that we have a very good sampling of these light curves. So I think you'll hear more about imaging, supplemental imaging from Peter, but I'm going to go back to spectroscopy. Spectroscopy is required, really required for getting redshifts, measuring the redshifts, because that's one of the axes that we're interested in on the Hubble diagram, classifying these objects as type 1As. And also, as I mentioned, there's a lot of interest in using spectroscopic information instead of light curve information to get precision distances here. And so what I'm imagining is a kind of a follow-up network of supernovae discovered by these wide field imaging searches. And just to kind of map out how these kind of surveys work, in case you've never worked on them, is that you have a survey that basically takes pictures of the sky and then looks for a new event. And when a new event is found, there's a light curve is generated of them as they grow in brightness. A subset of these objects are triggered. So there's an entire kind of machine learning classification piece here to decide which of these things are likely 1As and to be followed up at different observatories. I think SOAR is an excellent candidate for supernova follow-up. I should say that these are low redshift supernovae, so you don't need a large aperture telescope to follow these up. You get an observation. Here's an example of using a spectral, getting the spectral information out of for the supernovae, and then once you have these data, you can do the science. In particular, the measurement of the growth rate, this F sigma 8. Another thing that you can do, which I am not talking about much here, but is very closely related, is actually making maps of the local velocity field. And making a map of the local velocity field through the conservation of mass also means that you're making a map of the density field. I think I will skip this because this is maybe a little bit too detailed about what kind of instrument that I want to follow up these, want to use to follow up these supernovae. But one of the instruments that I am thinking about is integral field unit spectrometer. And in terms of what kind of resources are needed to do this kind of follow-up, I showed kind of two scenarios, one a short-term scenario and one a long-term scenario, one kind of looking at discoveries by ZTF, the other one looking at LSST. With the follow-up of the ZTF supernovae, you basically need on the order of 1. I think actually the real answer is 1 plus epsilon 2-meter telescopes to be able to do the follow-up of those objects. Of course, with LSST, you have many more supernovae and you want to go to greater depths. So you would need more telescopes and a larger aperture telescopes to go for the higher redshifts. Although, as I mentioned before, you can cut down on this a bit and still get a very interesting result. And the idea is to refurbish older instruments, commitment of observatories, but also I think it'd be very interesting to do some instrumentation R&D. In particular, if we are going to be using multiple facilities, 4-meter facilities, we would still like to put the same kind of instrument onto the different telescopes. So it'd be good to see if we can come up with a good solution for a spectrometer that works on kind of different kinds of telescopes. And of course, we want to leverage on existing resources. There's DESI, foremost multi-object spectroscopy that'll be coming up, the Son of X Shooter, and SNFs, which is an instrument in Hawaii. But I think one thing that I want to emphasize is that traditionally, actually, I think up to now, in terms of all supernova searches, including dark energy survey and pan-stars, we go to the funding agency and say, this is very important science. We need money to discover these supernovae, but we get no money to follow them up. We just have to apply to telescopes, rely on tax to be able to get the time to follow these things up. And I think that in the next generation of surveys, we want to change that story and make sure that not only supernova discovery, but their follow-up are included in the funding model. And just a little bit of a propaganda that this importance of the peculiar velocity studies has been already noted in the community in the Cosmic Visions Dark Energy panel, which was written in 2018. So this is definitely in the radar of the US community and is in the reports that are being generated by the community. Now, in the remaining time that I have, I just wanted to shift into something a little bit different, although it's definitely related, that I mentioned the survey called TAIPAN, and there are basically two kinds of surveys that are planned for peculiar velocities at the moment using galaxies. There's this TAIPAN, which is going to use the fundamental plane distances. So they're going to look at kind of early type galaxies. And their plan is to get on the order of around 100,000 galaxies that are good for fundamental plane distances. This is an optical telescope using a starbug fiber positioner. So it is another focal plane with a lot of fibers on top of fibers on them. Although nominally this was supposed to start already, but there appears to have run into some technical problems. So I'm not quite sure what the status is of this. The other approach is to go into the radio, to do Tully-Fisher distances and actually measure the velocities of spiral galaxy arms in the radio. And they're planning to do measurements of about 800,000 galaxies. But there is another galaxy survey that a lot of us are involved in coming up. It's called DESI. And you can see that, DESI in total is way much larger scale than what I just showed you there. In total, DESI plans to observe 35 million galaxies. Now, there's a whole bunch of different kind of galaxy classes here, but I want to focus here at the lowest redshift, where there is this 10 million bright galaxy survey. It's a BGS survey, and it turns out that we can use these galaxies with some additional observations to do Tully-Fisher distances and fundamental plane distances. So even though this is not core science of DESI, this is something that we are applying to do. And so recently there was a call for a secondary target program, and we put in a proposal to do those additional observations that will allow us to get distances for a subset of those BGS galaxies. So it requires a modest additional fiber allocation from DESI, 1 million. So that's kind of the amazing thing about these multi-object spectrographs, that 1 million is modest. And you can see that the numbers of galaxies that we can get with DESI for peculiar velocities it's not orders of magnitude, but it's factors greater than what people have used so far. These are numbers that are larger than the ones that I just presented for TAIPAN and for Wallaby. So this DESI itself can produce the largest peculiar velocity catalog better than what is being planned otherwise. And here's some projections for what can be done with in terms of the measurement of F sigma 8. In black here is basically the redshift space distortion, that measurement that you would naturally get from DESI, and in red is the improvement that you would get using peculiar velocities from these fundamental plane and spiral galaxies. And also plotted for reference are the 3 different gravity models. So, we're not getting into the 3 or 4 sigma kind of discerning distinction in the measurement, but we are making a big improvement in those in making those measurements. Another idea, which I will attribute to Colin Howlett, is that there is also an opportunity to test theories of gravity by seeing how gravity affects different scales. So here on the left-hand side, we've basically taken all the information and collapsed it all together into an amplitude to see how strong, what is this relationship just in terms of amplitude, or the ratio between density and velocity. But if you break this thing up into different K modes, you can actually start to get some signal to noise here. And the idea is that maybe we can actually notice that gravity seems to have a different behavior as a function of scale. And that would be another smoking gun for the fact that general relativity may not be the true law of gravity. Okay, so I am going to conclude now by saying that peculiar velocities are a powerful probe of growth of structure and gravity. And type 1a supernovae really fill in a low redshift niche where you actually have great leverage to test different theories of gravity and cosmology. And supernova 1a peculiar velocities are enabled by these new imaging surveys that are going to be producing large numbers of type 1a supernovae at low redshift less than 0.2. But the discovery is not enough. We need follow-up, in particular spectroscopic follow-up. And it's a modest amount of follow-up in terms of the sizes of the telescopes, the numbers of telescopes, and we need to make sure that we have the right instruments on those telescopes. And kind of a final conclusion I want to emphasize is that I described the SNOMAS process, which is definitely an American process, a US process. However, the international community is definitely invited to participate in the process. I will say that I was just in a meeting yesterday where there was a Brazilian in the room. And so I really encourage those of you who are interested in having a voice in directing where science goes, at least in terms of the United States, to join in. And I provide you with a website for the SNOMAS organization. So I will end there and take questions now.
Thank you, Alex, for the very interesting talk. We now have time for questions from the audience. If you joined us on YouTube, you can ask your questions in the comments section, and I will redirect them to Alex. So if you're here in Zoom, you can ask your questions directly. So,
Well, may I start?
of course, go ahead.
Well, first of all, Alex, fantastic, really fantastic talk and idea. So it's for me especially interesting to see a revival of peculiar velocities, after all the effort we did in the 90s, which were handling those 20% errors, which was tough. I do have a couple of questions about that. I mean, first of all, how much invasive would be if you build a network of telescopes in the Southern Hemisphere? Do you have any idea how frequently you would request time from, what kind of a model could you imagine? Use only the American time, get the Brazilian time in SOAR, for instance. How will you imagine that?
Well, I'll say that so first of all, there aren't going to be enough supernova discoveries to saturate a telescope, okay? So kind of the ideal thing in my mind is actually to get, okay, I'll say that one thing. I'll also say that the peculiar velocity constituency is not the only transient group that's interested in doing transient follow-up.
Of course.
So what I think would be ideal in my mind is for our community, the peculiar velocity community, to team up with other communities, transient communities, and actually get dedicated telescopes. However, I think that's also unrealistic, and I also think that we will need to go to apply for time at kind of open observatories. And I think that SOAR is a particularly interesting example of that, because I know that there's a lot of activity or thought in using SOAR as a follow-up instrument of LSST discoveries. You must be aware of this, and that they're actually building an infrastructure for that. So I think that in terms of the Brazilian community, I think that would be just okay. So then after that, there'll be a fight as to what actually to what objects that we want to target, and how much time that SOAR actually devotes to the follow-up of transients. So I think that's kind of a way that we can imagine having Brazil contribute to this program.
Well, I mean, I have no hidden agenda. I was just asking about the frequency. Another question, I mean, I'm surprised about this cadence thing. I thought supernova was one of the main targets for LSST. What changed? I mean, what was the...
Okay, so there's nothing that really changed. The thing is that there's two surveys in LSST. There's the wide, fast, deep, and there's the deep drilling fields. And the deep drilling fields are kind of what were thought of for supernovae. It's a classical, we're going to look for high redshift supernovae and measure the expansion of the history of the universe as far out as possible. And those fields do have very good light curves. However, the supernova that I'm interested in are the ones that are very low redshift. And those are going to be discovered in the wide, fast, deep search, and that survey was not optimized for supernovae. However, I will say that I am kind of optimistic because the project, I think, was a little bit surprised by how poor those light curves are going to be. So and there is a lot of there's kind of the committee that's going to be making the decisions about the ultimate observing strategy will include supernova people. So hopefully there will be a good conclusion from that.
Just a final question for me. I mean, how deep will LS4 go?
How deep will LS4 go? So I'll let Peter answer that. But really, the answer is that it's going to be basically equivalent to what ZTF is doing. So I think what we're talking about is, at least in terms of completeness, to a redshift of 0.1. So
you don't have to really rely on LSST. You can do a lot of science just with LS4, right?
Yes. No. Yes. I mean, so I don't. So I think that I have not formed a politically correct answer to that.
We are not recording.
I think this is on YouTube or something like that. Because I mean, the obvious question that will come up is, why do you need LS4 if you have LSST running at the same time? And I think that really the point of LS4 is not only to fill the niche of peculiar velocity surveys, but for the broad transient community who's interested in fast transients.
And brighter objects too, because we were thinking about falling asteroids and we couldn't do it because it was kind of a bright, it saturates pretty quickly. No?
Yes, exactly. And then the saturation of the very bright objects as well.
Okay. Thank you, and thanks for plugging in Peter's talk. So that's perfect. So we're going to have a perfect follow-up, followed by the director of the LSST or the deputy director of LSST.
Yeah, so you can have us minnows talk, and then you can have the big fish talk in a couple of weeks.
All right. Thank you.
Okay, now I'll pass the floor to Miguel. Miguel, go ahead.
Hi, Alex. Thank you for the talk. So I have also lots of interest in this field of supernova peculiar velocity. I have a few papers on that. And I have a question, but before that, I'm glad that you're also interested on this gamma parameter, which is fundamental physics parameter, as you pointed out. We have actually forecast for gamma on LSST, directly forecast on gamma, using only supernova velocities, which you might find interesting. But my question now is, in the beginning of the talk, you said that F sigma 8 is a fundamental parameter, but actually peculiar velocities measure is sensitive to H times F sigma 8, right? So the Hubble factor times F sigma 8. But you say that you find a cancellation in the process that you cannot measure H this way. I find that at odds with what I find, because this cancellation for me only happens at the limit of low redshift, which means that you cannot measure H0, for instance, with that. So if you try to solve the H0 tension with the peculiar velocity of supernovae, it's impossible. But at any other redshift, the cancellation is not there. So you could measure H of Z over H0, which is the E of Z function. You don't agree with that?
Yeah, so so what I described is exact only if you assume something very linear, the linear thing. And actually what I was imagining practically is that, you know, we would actually have to assume, actually, we're going to have a lot of supernovae beyond just these at low redshift, and that we would actually rely on a cosmological model for the background expansion evolution. So that, you know, in my mind, actually, I was imagining that we would do a simultaneous fit of kind of omega mass, omega lambda, W, and peculiar velocities, where the high redshift supernovae would basically pin down kind of the expansion parameters, and then the low redshift ones, handle the peculiar velocities. So in my mind, I was not imagining a perfectly model independent way of handling the background. And I have not thought about smart ways of trying to handle the background expansion in a more model independent way.
So yeah, I think, I understand, we can discuss this in more detail later, but I think it can be done. It's you only have to assume that you have a smooth distance as a function of redshift. As long as it's smooth, it's fine. You don't have to assume any cosmological parameters. Now, yes, if you allow it to be any crazy thing you want, then of course, that much of model independence, I agree with you, is impossible. But only assuming a smooth function, I think we've shown it is possible to do it.
Well, I don't know if we're going too technical into the details.
Yeah, I think you're going
to.
But
I will say that you would want to make sure that whatever smooth function that you have does not have embedded in it H information.
Very good. And I have another question, if I can, Rodrigo, is that you're talking about the need for follow-ups for this supernovae, right, from LSST, right? And I wonder if other surveys which do a different thing, which are not spectroscopic surveys, but which have lots of narrow band filters. So there are a couple of surveys going around. There's this BAO survey and this Havalambre JPS survey, which has around 50 filters each. And therefore, they can do very good photo Z. They are not spectra, right? They are coarse spectra. Do you think this could also be useful for doing as follow-ups for the SST detection, because they have very bad cadence?
It depends on what your objective is. If your objective is to do classification, I think they're good. But if you want to, you know, one of the ingredients in the cosmology is actually to get the redshift. And they will not be able to get precise enough redshift. And the error bars will be too large to, or the error bars will be large enough so that they'll become a significant part of the entire error budget of the peculiar velocity measurement. So I don't think you want to get the redshift of the objects that way.
And if I may, one very quick question as well. So as you said, you know, the survey strategy for LSST for the fast and wide survey is still, you know, it's very suboptimal for supernovae, right? And you said maybe you're only going to have a final answer by next year, by December next year, right, when the committee decides. Are there any public notes on how is this progressing from outside the collaboration, or is this only kept inside the collaboration? I mean, different possible strategies that could be used on to correct this lower redshift supernovae?
So I don't follow this completely, but I think everything is open. This process is being led by the project. It's not being led by any collaboration. It's being led by the project. And the project has been providing sample survey strategies and actually results from sample survey strategies. So the collaborations have been taking those in and running and processing them and making projections as to how this affects their science. Early on in the process, certainly the DESI collaboration started playing around and saying, well, if we do this, we can do much better. And we fed that back up into the project. So it really is the project that's leading things, and I don't think that there's anything private at the moment. I don't know that how the committee will work though. There's been I believe that there's been a call for input to the committee, but I don't know if they're going to be making public how they make their thinking process.
Okay, thank you.
Thank you, Miguel. I think we can start, we can wrap up. I don't know if anyone has any question. We are a little bit behind schedule already. Okay. Well, so just some comments. This presentation will be available on our website and in his YouTube channel. And also for the next week webinar, we will have Peter Nugent from the University of California, Berkeley, talking about the LIneA Schmidt Southern Survey. Thank you everyone for attending, and a special thanks to Alex. Thank you very much. And
okay, well, thank you for having me, and I look forward to seeing you somewhere in the world soon in person.
Okay, that's amazing. Thank you. And everyone have a great day and see you next week. Bye-bye.